Hello, everyone, and welcome to another edition of CEO and Market Expert Interviews. I'm your host, Lucian. Some of you know me as Triangle Investor from X. Today, we are covering ASP Isotopes, a very interesting company in my book. The company trades on the Nasdaq Stock Exchange under the symbol ASPI. I'm joined by their CEO, Mr. Paul Mann. Paul, thank you for coming to my show. It is great to have you.
Thank you for inviting me to come to your show. Look forward to
Thanks.
this.
Yeah, me too. You are for the first time in my show. Like I said, I would like to start with your origin story. Share us a bit of your background and how did you become ASP CEO, please?
Yeah, so my career has always really been in investing in chemicals and healthcare companies. I actually studied chemical engineering at Cambridge many years ago. I moved into banking, spent about 11 years at Morgan Stanley as an analyst, researching healthcare and chemicals companies. I then spent about 5 years working for George Soros, investing in healthcare and chemicals companies. Then about 3 years at Highbridge Capital, where I ran a portfolio of healthcare and chemicals companies. So that's been my entire career, is investing in these two industries. And late part of 2000, we found this group of South African scientists who had basically run out of money, and they were trying to build an isotope enrichment facility. And having spent 20 years looking at the industry, I recognized just how challenged the supply chain was in the industry, and we realized this technology could really change a lot of aspects of that supply chain and bring some great new products to market. So we spent quite a while diligencing it, and then we raised some capital, mainly from myself and friends, and we bought the assets of the company out of business rescue or bankruptcy in the US. And we then invested another tens of millions of dollars into this business over the last several years, and that's where we are today. We're on the verge of starting commercial production.
That's great story. Yeah. Okay, I will change my usual face-to-face format, and we will have Paul presenting the company with presentation slides. And after that, we will move to Q&A part. Paul, please give us your presentation.
Thank you very much. I'm going to put some slides up, and
Sure.
I'm hoping this will work. So hoping you're seeing the front page now. And so we're a Nasdaq listed company, so just look at these forward-looking statements, and the risk sections of our Form 10-K that filed with the SEC. That'd be great. So isotopes, what are we working in? What industries are we looking at, and where we're going to be? Well, we're looking at three main industries really: medical, which is for nuclear medicine essentially, and that's a huge market opportunity. We're looking at semiconductors, so next generation semiconductors that will enable quantum computing and artificial intelligence, and then nuclear energy. And so this is a huge new need for new nuclear energy. And ASPI has kind of three divisions. The first part is ASPI, which produces stable isotopes, and there we have 2 plants in South Africa. We're building a third at the moment. We have a subsidiary called PET Labs, and that's the leading producer of radioisotopes in sub-Saharan Africa. And they supply the majority of South Africa's radioisotopes. And the radioisotope has a short half-life, so you can't transport it very far, maybe 3 hours. And these radioactive drugs are produced very close to the patient where they're needed. And then last summer we incorporated quantum leap energy, where we're going to focus on producing the nuclear fuels of the future, specifically high-assay low-enriched uranium, lithium-6, and lithium-7. We've signed a lot of contracts in each of these divisions, and we expect ASPI to become cash flow generating, second half of this year. PET Labs is already generating free cash flow, and quantum leap energy is still some way off. In terms of our main milestones for 2024, our goal is to supply at least 2 additional supply agreements, but we've already done that, so maybe we'll try and do 2 more between now and the end of the year. We'll see if we can do that. And really to generate sufficient cash flow, sufficient revenues for the company to become cash flow positive. And then in terms of operational milestones, get our 2 plants up and running in South Africa and producing commercial product, and then start the construction of another isotope facility outside South Africa, most likely in Iceland, which benefits from very advantageous energy costs. So most of you probably know what an isotope is, but essentially isotopes are identical identical elements, but have different masses, different number of neutrons in the nucleus. It makes it very hard to separate them. You can't really separate them chemically. Some of the gaseous ones, such as hydrogen, helium, have slight temperature differences. But for solids like zinc, molybdenum, ytterbium, uranium, you really need to find some other way of separating them. And when we separate these isotopes out, they become very valuable. So if I take a bag of sand, a bag of silicon, it's probably worth $1 a kilo, something like that. When I enrich it in the silicon-28 isotope, it's $600,000 a kilo. For carbon-14, again, a bag of charcoal is probably $1 a kilo, that kind of number. A kilo of carbon-14 is $24 million a kilo. So we take these really basic elements and we convert them into very specialist materials that certain companies need. And we've got 2 plants that do that in South Africa, and we're building a third right now, and a fourth in Iceland. In terms of the supply chain, as I mentioned earlier, the supply chain is highly compromised. It's one of the most challenging supply chains of any material out there. And our goal is to make the supply chain easier so companies can grow and bring new products to market using the isotopes that we produce. We have two separation technologies to do this. The first is the aerodynamic separation process. The second is quantum enrichment. So the ASP process, basically, think about a traditional centrifuge. The tube spins around very quickly, creating a vortex inside. The heavier isotopes move to the outside. The lighter ones move to the inside. And that's how you separate heavy from light. For our process, we actually keep the tube stationary. And we spin the gas inside the tube. It's a stationary wall centrifuge. And that allows us to, again, separate the heavy from the light isotopes, heavier ones being on the outside, lighter ones being on the inside. The main difference of our technology is our capital cost is substantially lower than the centrifuge. Centrifuges cost billions of dollars to build, the size of football fields. You can't really do it on a small scale. Our plants, and I'll show you a picture in a few minutes, our plants are much smaller. We can produce kilogram quantities of very valuable, very specialist materials. We can also enrich light gases as well as heavy gases. Centrifuges can only enrich heavy gases. We can enrich light gases. And there's no real moving parts on our plants either, just a compressor. And so again, that makes it, the location or locating of these plants much more straightforward. Quantum enrichment is a technology our scientists developed in the late 80s. Basically, we pass a vapor of metal through a laser. The laser ionizes one of the isotopes. We collect those ionized isotopes on a charged collector plate. Again, both of these processes are very environmentally friendly. They're modular, so they can be scaled up and down as we need to. They're very cost effective. So let's start talking about the opportunity in nuclear medicine, first of all. So the nuclear medicine market is billions of dollars a year, and it's growing very rapidly as new drugs and new diagnostics come to market. There's been a huge amount of spend in this industry over the last sort of 20, 30 years or so. And we're really getting to a point where there's a real inflection point in how nuclear medicine can cure a number of diseases. This kind of shows the isotopes that are of interest to us in nuclear medicine. So carbon-14, molybdenum-100, zinc-68, nickel-64, and ytterbium-176. And you'll see each of these kind of stable isotopes is used to produce a radioisotope. And as I said, there's a real symbiotic relationship between ASPI and PET Labs. And PET Labs consume stable isotopes to produce radioisotopes, while ASPI produces stable isotopes. And they're used in a number of different end markets you can see there on the right-hand side. So molybdenum-100 is one of the isotopes we're more excited about. It's probably our largest commercial opportunity. This is the molybdenum-99 market's $4.5 billion a year market today, and it's growing. And molybdenum-99 it comes out of nuclear reactors, typically in Eastern Europe or other locations around the world. There's no domestic molybdenum-99 supply in the United States. And that molybdenum-99 has a half-life of 66 hours. Every 2.5 days, it's losing half its value. And as it decays, it turns into technetium-99, which is what's used to treat patients with or diagnose patients with. Molybdenum-100 is shelf stable. You can ship it in a FedEx package, and it can just sit on the shelf until you need it. And you can convert it to technetium-99 at the point of care in a cyclotron. We feel that's a much more attractive supply chain than the current supply chain that exists today. This is going to be a slow market for us to get into. Healthcare practices take years to change. The healthcare industry moved more like a glacier rather than a river. And so, you know, we're going to start focusing on this market, but it's going to be one that takes some time to get into. The isotope that I'm perhaps most excited about is ytterbium-176. So lutetium-177 is a radioisotope used in Novartis' drug called Pluvicto. It's a beta-emitting isotope that cures many forms of cancer, currently approved for prostate cancer. And there's two ways to make lutetium-177, the traditional route or the carrier-free route. And there's been a lot of problems with the traditional route, and many users of lutetium-177 are looking for more uses of the carrier-free route, which uses ytterbium-176 to create lutetium-177. Now, supply chain here is extremely challenged. I'm told there's about half a kilo available per year. It's all produced from Russia, and you know this sells at sort of $35,000 a gram. During the clinical trial for Novartis' Pluvicto, about 5% of patients died because they actually couldn't get the drug. They couldn't make the drug for the patient. And I'm told that, you know, right now in the US, sometimes patients are waiting up to 2 months to actually get access to the drug, again, because of supply side issues. And 2 months may not sound like a lot, but when your survival is measured in months, 2 months is actually quite a lot. So we hope to bring ytterbium-176 to the market during 2025. And we have a lot of interest from customers for that isotope. Then zinc-68 is another interesting isotope that is going to be used to diagnose patients that can use these lutetium and actinium-based drugs in the future. We expect this to grow dramatically over the next several years, and we expect our first plant in Iceland to actually be a zinc-68 plant, which will be funded by a customer. The smallest opportunity is actually our first plant that's going to be commercial, our carbon-14 plant. And there you can see a picture of an ASP plant. So each of those boxes is about 2 meters high by 2.2 meters wide, about a meter wide. And that plant will produce the entire world's demand of carbon-14. We've entered into a multi-year supply agreement with a Canadian customer for a minimum of $2.5 million a year. And as I said, we started processing the feedstock for that plant in December last year, and we expect to start supplying carbon-14 around the middle of the year. So this chart here just summarizes a lot of the opportunities we have in medical isotopes. So let's move on to semiconductors. So when you think about some of the challenges that the computer industry faces or technology industry faces over the next several years, it's about how do we process more data more quickly and more efficiently. And silicon has 3 isotopes, 28, 29, and 30. And the 29 isotope actually harms the conductivity of silicon. If we can remove that 29 isotope, the conductivity increases thousands of fold, and the heat transfer increases multiples as well. And so when you think about making iPhones smaller and faster and batteries lasting longer, making data centers need less energy to keep the cooling and operate on smaller scales. To make computers smaller, faster, cooler, we think silicon-28 is a great way of doing that. And we've signed our first agreement with a large semiconductor company to supply them silicon-28 during 2024. And the other isotope that semiconductor companies are interested in is germanium. The 73 isotope of germanium is similar to the 29 isotope of silicon. It harms the conductivity of germanium. And if we can remove that 73 isotope, the conductivity increases thousands of fold as well. So we're talking to a number of customers about germanium as well. I'd expect us to sign a couple more contracts for silicon and germanium between now and the end of the year. So in terms of our plans for growth, one of the challenges of being in South Africa is the energy situation. South Africa suffers from a lack of energy. There's load shedding, typically once or twice a day, where the lights just turn out. We have huge 1.5 megawatts of diesel generation capacity outside our bigger plant. And that costs a lot, and it hurts our cost of goods sold. And it's not good for the environment either. So having proven the technology in South Africa and built our first 2 plants, our goal is to take our ASP technology to Iceland and build a number of much larger, more efficient plants in Iceland, which will really bring down the cost of isotopes dramatically. If we can bring silicon-28, for example, down to a really attractive price, then maybe every iPhone can have silicon-28 in it to make it go faster and cooler. We've got to drive the price down. In order to do that, we have to improve our process, and we have to move to a cheaper location such as Iceland. So let's just talk about nuclear energy now. This is where I think most investors, or a lot of investors, are very interested right now. Our subsidiary called Quantum Leap Energy, which we intend to spin out later on this year. So, the problem is fairly well known. We need to at least double the amount of electricity generation over the next sort of 25 years and keep carbon emissions neutral in order to meet climate goals. That's not going to happen without a lot more nuclear power. The recent COP28, 24 countries have agreed to triple the amount of nuclear energy by 2050. And we think that's a great way of helping solve the environmental problem that the world is currently facing. We believe the future of nuclear energy is a small modular reactor, the SMR. And, some of the companies involved in the SMR space are TerraPower, which is the chairman, that's Bill Gates, X-Energy, which is Cam Garfassian, Oklo, which is Sam Altman, and Rolls-Royce. And these SMRs, think about an SMR as being, the Ford Model T of the motor industry. What made cars get really cheap was production line manufacturing. And traditional nuclear power stations have cost tens of billions of dollars, taken tens of years to build. You need huge transmission lines to get the energy away. SMRs are much smaller. They can fit on an acre piece of land or on the back of a truck. You can put them next to a data center or a factory. Think of it as like a 60-year battery that powers the location that needs the energy at an extremely low price. No need for large transmission grids, and it's really environmentally friendly. And the cost drops dramatically when you have these production line economics. The problem for a lot of these SMRs is that they need a new type of uranium called HALEU, high-assay low-enriched uranium. And right now there is no Western producer of HALEU. I think people were hoping to get it from Russia. Russia was intended to downgrade weapons-grade material to make it. That's no longer available. And so these companies have spent billions of dollars inventing these new nuclear reactors, and there's no fuel available for them. So, what do we do? Well, we believe we can help solve that problem with quantum enrichment. So we feel quantum enrichment is the most powerful of all the enrichment technologies available today. As I said earlier, we kind of vaporize a metal, shine it through a laser stream, and ionize one of the isotopes. This kind of compares quantum leap or quantum enrichment to other types of enrichment. So if you look at gaseous diffusion, and the important line here is a selectivity line. If you look at the gaseous diffusion, that's 1.003. That was what was used back in the 1940s and 50s. The world then moved on to centrifuges, where the selectivity is about 1.15. And that's the standard today of industry uses. And you'll see two laser-based methods here, AVLIS and SILEX, where the selectivity is, between less than 50, but substantially better than that of a centrifuge. Our quantum enrichment selectivity is greater than 50, substantially greater than 50, and that allows us to do more enrichment per stage of the plant, which really drives down the cost of enrichment. Here's quantum enrichment, a real-world experience. And so if you look at the chart on the right-hand side here, this is actually published as part of our Chief Technology Officer's PhD. This is the enrichment of lithium-6 and depletion of lithium-7. So the top chart is lithium-6 and 7. The lithium-6 on the left is about 7%. The lithium-7 on the right is about 93%. And after a single pass through our enrichment chamber using quantum enrichment, the light isotope lithium-6 is greater than 90%, and lithium-7 is below 10%. So that's for a light side enrichment factor, a beta, of 112. So 112 versus 1.15, that kind of shows you how efficacious this technology could be. And we're in the process right now of scaling this up. We're building our first plant in South Africa for ytterbium-176 using quantum enrichment. So what's happened to nuclear fuel supply chain over the last sort of 12, 24 months? Well, as you can see, all the prices have gone up for every component of the nuclear fuel supply chain. Uranium prices up 5-fold, conversion and enrichment up 3 to 5-fold. It's very rare to see a commodity increase by 5-fold and not see a supply side response. That kind of shows you where prices probably have to go before we see a material supply side response. So the world does have a real problem right now with supply demand. And I suspect 2025, 26, we're going to see buyers of uranium short, not being able to find what they need to power their nuclear power stations. How that plays out, I don't know. I don't have a crystal ball, but it's not going to be very good for the world or for the people in that region who need that power. Implications for HALEU, well, obviously HALEU prices are a direct correlation to the three prices I showed you earlier. You know, HALEU, if available today, would be probably $20,000 a kilo. Most of these SMR programs were designed when HALEU was expected to be, you know, $5,000 to $10,000 a kilo. And what you're seeing is, you know, a lot of the economics of these projects come under question because of the price of the fuel. So, you know, one of the things we're excited about quantum enrichment is that because the enrichment factor is so high, we believe we can take other people's depleted tails and convert that straight into HALEU. And that will have a really huge impact on the price of us producing HALEU, because rather than having to pay, you know, 50% of the price for feedstock may well come for free. And that will really kind of change the price of HALEU and allow us to position HALEU so that anyone in the world can use HALEU at a price that's a discount to hydrocarbon-based energy. And that's what the world needs, is to have cheap nuclear power to make it available to all. This bottom chart here just shows, you know, the three isotopes we're looking at in nuclear energy. So I guess finally, to summarize, you know, our company, we're leveraging a proprietary proven technology that's been developed over the last 20 to 30 years in South Africa as part of South Africa's nuclear program. Our end markets are benefiting from multiple secular and geographic tailwinds. And I say our first plants will start up in the next sort of few weeks or months and start producing free cash flow around the middle of the year. So I guess I'll stop there and take any questions if that's okay.
Sure. Thank you for this presentation. It was a great presentation. Now we will move to Q&A. The first question is, can you draw parallels with your technology versus Silex technology?
So I don't really want to talk too much about competitors' technology, and quite frankly, they haven't shown the world much about what they do. We know very well what they do. Our scientists actually sold them our predecessor company built the lasers and sold the lasers to Silex, so we know exactly kind of what they do. So first of all, they cool down their uranium to a very cold level, and they use UF6 gas, and they expand that gas through a nozzle, and they hit it with a different type of laser. And try and remove the U-235 that way. We heat up. We take straight metal, and we heat it up to about 3,000 Kelvin to a vapor, and we pass it through a different type of laser, different wavelengths and different structure, and that allows us to excite or ionize the U-235 elements. Then we catch them on a collector plate, basically. So there's some differences between the two. You know, if you read the literature, the selectivity of Silex is about sort of between less than 20, whereas our selectivity is greater than 50. So it's a bit of a difference.
Okay, second question. Do you have some longer-term revenue projections for the company, and how much of those revenues will come from medical, how much from energy, and how much from industrial use?
Well, we do have internal targets, but we haven't shared them, so I can't really provide you with those, I'm afraid.
Yeah, sure. Next one. How much skin in the game do you have personally, and do you plan to buy more stock on the open market?
So I'm the biggest shareholder of the company, and I think I own about sort of 15% plus or minus, and obviously can't talk about plans to trade in the shares that, you know, so I can't talk about that, I'm afraid.
Okay, fair enough. Next question. Do you plan to expand your portfolio to some new technologies, and if yes, what is your field of interest here?
You know, we feel we have two great technologies already. And so, you know, I think we will develop the two technologies we have to become better and more efficient. You know, every plant we build in ASP, we try to make it more efficient than the first. So our generation 4 plant, which is the bigger plant in South Africa, is about sort of 35 times the size of our generation free plant. And, the goal is to bring down the cost of production by about 50%. And our goal for a Generation 5 plant is to further bring down the energy by 50, maybe more percent, and make it bigger and better. So I think we'll keep advancing the technologies we have to improve them and to make it even more competitive.
Okay. Next question. What do you think quantum enrichment could be operational?
So is that when?
When? Yeah.
So our goal is to try and supply fuel by 2027. That's when our customers need it. Our plants are much smaller, quicker to build, cheaper to build. We get a much higher return on capital versus a traditional centrifuge where you don't get a return on capital traditionally.
Yeah.
But obviously it's very much subject to licensure and to getting permits from a government to be able to do it in their country.
Got it. What are the next steps for the company and the most important catalysts going forward?
Well, the most important next steps is to start generating free cash flow, which we expect to do, later on this year. And having got to the point where we're generating free cash flow, then we can start reinvesting that cash flow to build additional plants, and generate a very high IRR on those plants and generate good returns to shareholders.
Okay, Richard wants to know, how is the situation with skilled labor? Do you have trouble finding and keeping operators, scientists, and engineers?
So I wouldn't want to try and build this business in the United States or Europe. There, I think we would struggle to find the skilled labor that we need. In South Africa, actually, we found hiring qualified scientists and engineers extremely easy. South Africa has one of the strongest histories in nuclear engineering. 4 countries currently offer nuclear engineering as a degree. DOE has just sent 30 students to Northwest University at a cost of $30 million to study nuclear engineering because those skills are not available in the United States. When we acquired the company, we had maybe 7 to 10 employees. The average age was probably 60, mainly physicists, mathematicians, and a couple of engineers. Now we have about 80 employees. Of those 80 employees, 20% have got PhDs, half have got advanced degrees. We have a new, our head of R&D, our new head of R&D, Dr. Van Heerden. She used to be the lecturer in distillation technology and separation technology at Pretoria University. We have just hired 3 PhDs in fluorine chemistry and electrochemistry, again from the recent universities. And every year, we probably get the 5 top graduates coming out of university to come and work for us because they want to work for an American company in South Africa, get American stock options. And it's been very easy to get strong talent coming, strong young entrepreneurial talent coming out of local universities. And I'm very, very happy with what we see. Not a single employee has left our company on their own accord.
That's great to hear. Mark wants to know, when is the facility in South Africa that you are building right now? When will it start operations?
So our first plant we're processing the feedstock for that first plant already. So we are essentially in operations already. It takes 6 months or so to process the first batch of feedstock from being released out of a nuclear rod to becoming final product. And so we're in the middle of that process right now. Subsequent batches will take about 3 months, much faster the second and third batches are. And the second, much larger plant is in kind of the cold commissioning stage right now. And we're awaiting feedstock for that plant. And so again, imminently.
Yeah, I have a similar question. Plant in Iceland, you mentioned during the presentation. At what stage is that? Is that in the plan, in the works? What's the stage?
Yeah. So we've got 3 out of the 4 government permits we need to build that plant. We're waiting for the 4th permit. I would expect we start building that plant, around the middle of this year, back end of the first, maybe in June. And when I say building, we'll start doing the design work and planning for it. And the goal would be to have that plant operational by the middle of next year.
Okay, 2 more. Is South Africa safe jurisdiction with growing uncertainty in Africa?
Stable, boring countries don't sell newspapers. So, newspapers generally make things look more exciting than they actually are. Driving around South Africa, there's obviously certain parts of certain cities I wouldn't go to, particularly at nighttime. but that's the case with a lot of cities in many countries around the world. The country suffers from high unemployment, and there's a lot of social problems relating to that, obviously. I guess the energy situation is probably the worst of the most significant of the issues that we have. That's easy to fix. It just costs a bit of money. We have a large diesel generator, and that makes sure we always have 24/7 power to our plants. So, I mean, in general, I think there's pros and cons to being in South Africa. One of the pros is that we have a very supportive government and a very supportive nuclear industry there. We have good dialogue with our regulator, who visits our plants frequently. It's very hard to get access to the regulator in both UK and in the United States. If I want to speak to the regulator in South Africa, I can just pick up the phone and speak to her. So we have a very supportive government, and we do a lot to help the country as well. I mean, we employ a lot of people now, all of whom have got higher than average wages. We've invested a lot of money into the country. We're adding another $10 million in South Africa's nuclear medicine industry. We give away all of our drugs to children under the age of 18 free of charge. It's not appropriate for a child suffering from cancer to have to work out how they pay for that drug. So we do that free of charge. And so we've built up a lot of goodwill with government entities as well. So listen, there are pros and cons. But longer term, we want a diverse manufacturing base in a number of locations. And so it's right for us to build our next plant outside South Africa.
Sorry, I got two more, not one. How many of big holders with 2% or more do you have in your share registry? I mean, is there any? What is your share strategy? Your share registry is looking like?
Yeah, I don't know about 2% because the cutoff where investors have to report filings is 5%. That's where people file 13Fs and things. So I don't know. I couldn't say. And obviously people investors will be filing their 13Fs for March 31 in about 5 days' time, and so we'll see who owns our shares then.
Okay, final one. What is your cash position, and do you have difficulties in raising money?
We've actually got the strongest balance sheet we've had since we started the company. So we've raised $30 million more in the last 12 months. So we have a very healthy cash position. We're publishing our 10Q in the next few days, so you can look there to what the cash position of the company is. But we haven't had a problem raising capital. And I said the balance sheet's never been stronger. So yeah, it's good.
Good to know. That was Paul Mann. Thank you very much, Paul, for coming to my show. I wish you luck with your work in your company, and I hope we will catch up sometime soon again. Thank you very much, sir.
Thank you for your interest.